Let's dive into the first topic of the course. That is the combinational logic. A combinational circuit is a logic circuit whose output at any given moment depends solely on the value of its inputs. This slide shows an example of a combinational circuit. It is made up of basic logic gates and, or, not, and potentially derived ones, interconnected appropriately to perform a given function. To satisfy the condition that the output at any given moment depends solely on the current input values, the combinational circuit establishes a data flow from inputs to outputs, thus forming a directed acyclic graph. The first need that arises is to identify a formalism to represent and manipulate a combinational circuit easily and automatically with a computer. Unfortunately, the graphical representation does not help us in this regard. Instead, the switching algebra studied in the previous videos is precisely the tool we are looking for. In fact, it is a mathematical and textual formalism that can be easily handled and manipulated using an algorithm executed by a computer. Therefore, we use switching algebra to represent the implementations and specifications of combinational circuits. As shown in this slide, an implementation of a combinational circuit can be described using a Boolean expression. In the example, the expression on the right textually models exactly the circuit that is graphically represented on the left. More specifically, the inputs of the circuit are represented by logical variables. This also applies to the outputs, since they will eventually serve as inputs to some other downstream circuit. Each basic logic gate, and, or, and not, is then represented by its corresponding operator in switching algebra. In this slide, we show the graphical symbols of the three basic logic gates and the truth tables of their corresponding logical operators. The other derived logic gates, NAND, NOR, XOR, and XNOR, can be represented using Boolean expressions. For NAND and NOR, it is sufficient to negate the expression that produces the logical product and the logical sum, respectively. In the case of XOR, we derive the expression using the first canonical form, and finally, for XNOR, we negate the expression obtained for the XOR gate. If we represent circuits using logical expressions, it becomes intuitive to represent a specification of a combinational circuit using a truth table. Indeed, the specification describes only the behavior at the terminals, that is, the output as a function of the inputs, while a circuit represents a concrete implementation of that specification. This is precisely the relationship between truth tables and expressions. Extending this analogy, we observe that for a given specification of a combinational circuit, there can be infinitely many possible circuit implementations, just as there are infinitely many expressions that can represent a given truth table. Given a truth table, we can also refer to a row more compactly by using the decimal number obtained by converting the bit string corresponding to the inputs. In other words, we label all rows with sequential numbers starting from 0. Here is an example of a truth table. As you can see, we can number the rows sequentially from 0 to 7. The truth table has a number of rows that grows exponentially with the number of inputs. A more compact version consists of specifying the onset, defined as the set of decimal values corresponding to the ones of the function, that is, the minterms. Dually, we can specify the offset as the set of maxterms. Onset and offset form a partition of the truth table. Here is an example of a truth table along with the corresponding onset and offset. As you can see, the onset is composed of the values 1, 2, 3, 4, 7, meaning the row numbers for which the function has a value of 1. We define the offset in a similar way. On the right side of the slide, we also show three different notations for specifying onset and offset. We will use them interchangeably throughout the course. Sometimes, the output of the function is not defined for certain input configurations. These configurations are called don't care conditions and are represented in the truth table with a horizontal dash. The don't care set represents the set of all such indifference conditions. Here is an example. Inputs 2 and 5 represent the don't care conditions of the function. The onset, offset, and don't care set together form a partition of the truth table. Therefore, To represent a specification compactly and completely, it is necessary to specify at least 2 out of the 3 sets. Typically, we specify the on set and the don't care set. Let's take a moment to analyze the causes that lead to the generation of a don't care condition. Typically, the function to be synthesized is part of a larger circuit that provides its inputs through upstream logic and utilizes its outputs in downstream logic. Here is an example. The don't care conditions arise due to the controllability and observability of the considered function by the upstream and downstream circuits, respectively. A don't care condition can occur when a particular input configuration is never applied to the function. In this case, we say that the configuration is uncontrollable. Let's consider the example from the previous slide, specifically the upstream circuit of the function f of a, b, and c that we want to implement. Here we show the 3 logical equations of that upstream circuit. We then compute the truth table, which has been merged into a single table. As you can see from such a table, only 3 configurations are generated on A, B, and C. These correspond to 1, 3, and 6. The other configurations, 0, 2, 4, 5, and 7, are never generated by the circuit and thus represent don't care conditions for the function f. A don't care condition can also occur when, for a given input configuration, the output of the function is ignored by the downstream circuit. More formally, this means the function's output is unobservable. Let's go back to the previous example, specifically the downstream circuit, which is represented here by the logical expression O equal to F or A. Do note that in all cases where A is equal to 1, the output O will be 1, regardless of the value of F. Therefore, F is unobservable when A is equal to 1. This implies that the don't care set due to observability is generated by all 3-bit binary numbers starting with 1, namely 4, 5, 6, and 7. Finally, the overall don't care set of the function is calculated as the union of all non-controllable and non-observable configurations. Identifying the unobservability conditions for a function is somewhat more involved than identifying the uncontrollability ones. First of all, we need to note that a 0 on an input of an AND gate makes the other input unobservable. A 1 on an input of an OR gate makes the other input unobservable. Similar considerations apply to NAND and NOR gates. NOT, XOR, and XOR gates do not have unobservability conditions. The observability analysis of a function must be carried out by considering the path from the function itself to the main output of the overall circuit. Here is an example. A 1 on the second input of the OR gate downstream of F makes F non-observable. Therefore, all input values where C is equal to 1 represent don't care conditions, namely 1, 3, 5, and 7. Next, we analyze the subsequent AND gate. A 0 on its second input makes the path from F to the main output O unobservable. To generate a 0 on this connection, we need both A to be equal to 0 and B to be equal to 0 simultaneously. This implies that 0 and 1 are also don't care conditions. In conclusion, the don't cares related to observability are calculated as the union of the 2 sets found in the analysis. So the overall set is composed of the elements 0, 1, 3, 5, 7,